Hello there. Welcome to the Off by One security stream. It is Friday, August 18th, and I just realized that the summer has like flown by extremely fast, which is just crazy. My camera is not working today, so you have a nice screen to look at, which I have up at the moment. So apologies for that, but it's going to be mostly demonstration stuff today anyway, as usual. I don't have a guest today. It's just me. And I said last week, I don't even remember what I streamed about last week, but I said that I would do this Friday a session on looking at off by one vulnerabilities. I thought that'd be funny. No, hey, it's the off by one security stream. Let's look at off by one vulnerabilities. It's due time. So another thing I'll say is if you saw my tweet, next Friday, I've got Jonathan Ryder coming back on. He's going to take us through a session called A Life of a Packet. And I believe so. When he came on before, it was a session on like C2, like building your own command and control, as much as you can cover in like 90 minutes anyway. And he said he would come back on and get a little more technical. Some folks were asking for some more technical stuff. So he is going to come back on, take us through the life of a packet, which it's funny because I had a project a long time ago that was similar. But I imagine what's going to happen is we're going to have a packet when it hits the wire, a packet comes across the wire, it hits your system and that interrupt occurs, like what happens at that moment in time when that packet hits your system and the driver gets involved? Like what happens? What is the life of the packet? And then like he's going to take us through some interesting kernel debugging and we'll look at some deep technical stuff, I imagine, around C2 related activities. So I think that's going to be a really neat one, and definitely for folks who want a more technical session, more than they normally are anyway. I think that's going to be quite a technical one. And then September 1st, so that's next Friday. Next Friday is Jonathan Ryder. 2 weeks from today, on September 1st, I've got one or two individuals from BC Security coming on, and they are going to do a session on looking at um, PowerShell Empire, called Empire Strikes Back is the name of the talk. But they're going to be looking at stuff with .NET and just kind of what they've been working on and some cool things you can that you can get into there. So I'm excited about that one. I'm not exactly sure what exactly we're going to be covering, but since it's the guys from PowerShell Empire, it's called Empire Strikes Back. We're looking at .NET and other things that we can do, C# and all. So they're also going to give away a seat to their course running in September. Yeah, thank you. Embracing the art of adversary emulation. So Empire Strikes Back, embracing the art of adversary emulation beyond PowerShell. So they're going to be giving away a free seat to their training that's running in September. And I believe they are allowing you to take that virtually, or you can go in person. You obviously would have to get yourself there, but you can sit the course in person or you can take it online. And that's a super generous offer from them. So I definitely will be promoting that. I'm not sure how we will give away or they will give away that seat. Maybe it'll be a trivia question. Maybe it'll be a quick challenge. Maybe it'll be randomly selected, but you definitely will have to be present on this stream live to be able to qualify for that seat. So that's pretty cool. I think it's $3,000 class, so it's very, very generous. Okay, that's all I've got scheduled for now. Let's get into our session for today, off by one. So when you think about buffer overflows and general exploitation techniques, we always look at, oh, let's see here. So does my internet seem okay to everyone? If whoever's listening right now, just punch up like, have I been dropping in or out, or has everything been okay? Just want to make sure that the quality, because I can always switch over to a secondary connection that I have if it's not going so well. It takes a moment for your comments to reach my screen. I don't know why there's a delay. Um, you are clear. Cool. Thanks, Robert. So it sounds like I'm good. Okay. So it must be the one individual. Fine so far. We're good. Okay, perfect. Thank you. So back to my point. We think about for overflows. If you look at the screen right now, we have, a bunch of A's and we overwrite the return pointer maybe. And then when the ret instruction executes, we get 41414141 up in the instruction pointer. Okay. It's really easy to understand as to why that leads to code execution very easily. And as I'm talking, I'm going to grab bear with me for a moment. I'm grabbing my uh, tablet, my drawing tablet, so that I can draw something on the screen real quick, because I find that even though my art skills are terrible, it really does help with understanding what's going on if we do draw this stuff out. So I just plug that in. No, don't connect to the host. Got my old host here, so we'll just use this guy. Here's paint. Let me make sure that the pencil works. Where is my pencil? I am all discombobulated today. As soon as I find my drawing pen, I will show you exactly what I mean. Because the first thing I want to do is just draw up a simple example of a buffer overflow vulnerability that you've seen a million times. And David Bombal just had me on the other week, and we did a session on that as well. But I know most of you are very familiar with buffer overflow. So right here, I'm drawing on the screen. We've got we'll just say that's the stack, right? And we've got this buffer up top. So we've got this buffer up here. I'll just put buff. And then below that, we might have a frame pointer. So I'll put FP for frame pointer. And then below that, we've got the return pointer. And if we get something like a stir copy call, which is a banned function, if its destination is that buffer, if the buffer is only, say, 16 bytes, and we just continue to write, it's going to keep writing downward, and we're going to overwrite that return pointer with A, right? That results in 41414141 being where the instruction pointer goes to execute code. Very simple concept. But my point of explaining this is that it's really easy to understand as to why you get code execution in that case, right? Because you've literally overwritten a pointer where redirection of execution is going to go to that address. So therefore, if you allocated something at that address, in this case 41414141, you will execute what's there as long as permissions are good. Very easy to understand. But now we're talking about a bug class known as off by one. So imagine in this case, now this isn't an off by one exactly what I'm going to explain here, but let's say that you only get the ability to write 1 byte out of bounds. In this case, if you could only write 1 byte out of bounds of the buffer, you're only going to take up 1 byte of the frame pointer. Like, that's it. So you think about that and you're like, well, how would I get code execution out of that? That seems not very useful when you only get a single byte. So a couple things coming up here. Let me see if I missed a question. Uh, Low-level exploitation in a real-world application. Any resources? um, Practice low-level exploitation. I mean, these sessions obviously that I've been doing are useful from that perspective. I got to get better about posting up the POC code when I do have it, or the target vulnerable program. But this stuff we're doing here in this channel is a good example. I would also go to, I mentioned this before, I'll type it up in the chat, corland.be. I just typed it in. It'll take a moment to display, but corland.be, that is Peter van Ickhout from Belgium's. He's Corland coder. It hasn't been updated in a while, but Peter used to, and the Corland team used to do constant updates on that site, and they've disclosed so many useful teaching examples and exercises where the vulnerable code might be there, and you can download it, you can follow through the walkthrough, really well documented walkthroughs there. Obviously SecurityTube is a good place. I always recommend people go to exploitdb.com because there's so many vulnerable programs there, and you can download the vulnerable programs right from the site, put it onto a virtual machine, and there's a vulnerability in there. So you're not wasting your time. So treat it like a 0-day. Pretend that you don't know. And obviously, if you just download the vulnerable program, you don't know where the vulnerability is. So your goal would be to find the vulnerability via fuzzing, via static analysis, reversing, however you want to do it. If you can't find it, look at the answer, because the exploit is right there next to the vulnerable program. And once you look at the answer, still go back and try to find it yourself or fuzz it to trigger it, and then work your way through exploitation of it, and then download the next one and the next one. There's like a never-ending supply of real-world target vulnerable applications with the answer right next to it. And obviously, you want to get good enough to where you don't have to look at the answer anymore. That's your goal. When will you do modern exploitation sessions? Can you elaborate? Like, what are you looking to see there? We had a couple sessions recently, one with myself and Connor McGar. We were looking at getting token stealing in the kernel using the previous mode technique that is still possible in a lot of cases. Microsoft did patch that back in December, but that was when we did that session. That was literally the week or two before Microsoft patched that example. I had Chompy on a few weeks later after that, and we looked at binary diffing, a one-day patch analysis of a TCP/IP.sys driver vulnerability, and we looked at weaponizing that to trigger the vulnerability. That was a brand new 2023 CVE as well. We've done a couple of those. So whenever there's a good opportunity to do one, we'll absolutely take a look at one. I know one of the ones I want to do soon here is I'd like to just take a Patch Tuesday, and maybe we do it on Patch Tuesday, but maybe we just wait till that Friday so I'm consistent with my scheduling. But where we just go and start looking together at the patches to see if we can find anything. Now, obviously, we won't be able to weaponize it within an hour or two. That would be ridiculous. But maybe we can find the vulnerability and we can look at potentially how we would go about triggering that vulnerability. Um, the problem with that is that when you're doing one-day exploitation, when you're doing patch analysis, it is extremely time consuming. Most of the vulnerabilities that you would be looking for in the Patch Tuesday patches, most of them are not exploitable. Most of them are like theoretical, or maybe it's potentially exploitable, but there are mitigations that will prevent you from being able to exploit it. A lot of the times, that's the problem. Like Microsoft still is going to go patch it because theoretically you could exploit it and it needs to be fixed, but it's not actually exploitable because those mitigations are blocking you. So you run into that problem a lot. So when you're doing one-day patch analysis, it is very time consuming and very frustrating and humbling. You will find that a lot of people end up giving up after doing it for a few months because you're never able to actually weaponize anything. And the reason for that might be skill set. You might not understand how to go about doing it, or you might just be getting unlucky. I guarantee you that at least one or two of the vulnerabilities patched each Patch Tuesday are exploitable. It's just you've got to put in the time and the blood, sweat, tears, all that stuff. So that I think that would be a cool session. So I'll definitely try and get one of those scheduled, maybe for September or October. All right, so let me get back on here. And this example I'm about to show, I mean, this is a vulnerability or a bug class known as Off By One, which if you discover an Off By One vulnerability, they're still potentially exploitable if you can get it working. So it's absolutely, um, contemporary. So back to my point here, if we overwrite a return pointer or a function pointer and it gets called, then we clearly see why we get code execution, right? There was in back when Flash was a thing. Remember Flash? Seems like so long ago, and we thought Flash would never go away. There was a CVE that we taught in one of my exploitation classes where it was a use after free vulnerability in the browser. And with that use after free vulnerability, the only thing you could do with it was overwrite 1 byte in memory. You could choose the address where you're going to overwrite memory, but you can't choose what's written there, and you can only overwrite one single byte. Now, this was not an example of an off by one vulnerability, but it's similar in that you can only overwrite one single byte. And I remember back when I first looked at that CVE, I'm like, man, that's going to be tough. If you can only overwrite 1 byte in memory, how are you going to get code execution from that? Well, this is where our good friend Flash at the time helped us. I think a lot of people didn't realize why Flash was so evil when it came to exploitation if you hadn't really worked with it. So you can write your own Flash modules using ActionScript, which is yet another language. So you use ActionScript to build a shockwave file, an SWF file. And with that malicious Flash file, once Flash is executing, if someone loads your Flash file, it's going to do whatever it's allowed to do. Now, it's supposed to be contained at the time, like not necessarily sandboxed, but it's supposed to be contained and limited in what it's capable of doing. But one of the things we were able to do with this particular vulnerability is with Flash, you can't. I'm going to be careful with my wording here. Not that it really matters because it's Flash, but with Flash, you can't do certain things like triggering stuff that's in the DOM, the browser DOM itself. What you could do though is you could make an external function call to a JavaScript function. And that JavaScript function was the one that would trigger the use after free vulnerability, allowing us to overwrite 1 byte in memory. And in that example, we would do heap spraying using the Flash object. So we basically create a bunch of sound objects in Flash of a very big size, and we would do a heap spray. That's what my talk was on last week, heap spraying. And we would extend the heap way down to predictable addressing, just like I explained last week. If you're not familiar with heap spraying, go look at the session last week because I really went into detail as to why with ASLR on, heap spraying still works so well. And it's because you're extending the heap so far that you're getting to predictable addressing due to memory segmentation. We have to maintain segmentation so things aren't colliding with each other. So we could use Flash to spray the heap using sound objects, getting to a predictable address. When we trigger the use after free vulnerability in the browser, it would then overwrite 1 byte of memory in the sprayed memory that we spray with Flash. Specifically, we overwrite the most significant byte of a size field of one of these sound objects. So we overwrite the most significant byte. What that does is it gives Flash, or it gave Flash, access to almost all of userland memory. So Flash could then go and it was parsing through memory looking for MZ or MZ from Mark Spakowski, which was the PE header, one of the magic numbers there. When it found that, it knew it found the shockwave file, and then you basically switch over to relative virtual address offset ROP gadgets. So you would, one more time, you would, in order, you spray the heap with Flash using sound objects, get to a predictable address, make an external function call to the JavaScript function from Flash, trigger the use after free vulnerability, overwrite 1 byte in memory in the sprayed memory, which was the most significant byte of the size field of one of these sound objects, which would then in turn give Flash access to almost all of userland memory. So then it would parse through userland memory looking for MZ for Mark Spakowski. Once it identifies the load address, it can then use relative address offsets to populate the ROP gadgets. Super cool stuff. That was one single byte. The way that you got code execution was via Flash. So this, now we're going to go 100% over to Off by One. Off by One, you don't get to control what address in memory you are overwriting. You can overwrite, basically, it's typically the adjacent byte in memory, 1 byte past a buffer or an array, 1 byte. So the big question is, if I can only overwrite 1 byte in memory and I'm limited to where it's out of bounds adjacent to my buffer, what can I possibly do with that to hopefully gain code execution? And that's what we're going to walk through a little bit here. I have some experience in exploiting heap and glibc. Our allocators and exploitation very different. Our Linux background can help to understand heap internals of Windows. So yeah, good question. The question is basically if I have a good understanding of how the heap works on Linux, like ptmalloc and tcmalloc, does that apply to Windows? Does that map over? Absolutely. A lot of the concepts are very similar, like the idea of a doubly linked list on the back end. So on Linux, you've got different types of heaps. You've got the back end doubly linked heap. You've got, and subsegments within the heap, you've got the front end allocator, which historically it was always called fast bins on Linux, which are still there. But then for optimization, they started coming out with things like thread cache, basically Tcache bins. And these Tcache bins, because a long time ago we had a global mutex, and so if you had multi-threaded process, you had this global mutex that you had to wait on. It's very slow. So what they did is they started giving every thread its own heap, and with each heap you have its own set of bins, these free bins, so that you could use them. They're specific to that thread. Historically, we know that every thread gets its own stack segment, right? Every thread gets its own stack segment, but it wasn't the case where every thread got its own heap. But that's what we try to do with modern allocators. And there's a little math you do. It's based on the number. If you're on 32 or 64 bit, multiply by the number of cores on your processor, and that's how many heaps you can support But yes, back to the question, a lot of those concepts map over to Windows. Windows, it started off where you had the back end doubly linked free list, same thing on Linux. And then you had the front end allocator, which is called the look aside lists on Windows. On Linux, it was fast bins. On Windows, it was look aside lists. And they're pretty much the same. They're singly linked. They can only point forward. There's no pointer protection like you have with safe unlink because there is no unlinking. And there's very simple exploitation techniques that you could use against the front end allocator. Well, Microsoft, as of Windows Vista, came out with something called the low fragmentation heap, which the low fragmentation heap was something that had to be triggered. 18 consecutive allocations of a specific size would trigger LFH to service that size. So any chunk of that specific size that LFH got triggered would then be serviced by the front end allocator. And you might ask, well, why do we have a front end allocator and a back end allocator? Well, on the back end, it's slower to get something out of it. There's got to be a heap manager that manages all the memory on the heap. And it can get a little bit complex as to how it works, but it's not too difficult. And the idea was that on the back end allocators, on the back end heap, you want to worry about fragmentation. You want to keep things clean. We all know what fragmentation is. We know what defragmentation is on the hard drive and such. We want to make things clean. And there's a rule on the heap, and this applies to Windows and Linux, which is no two free chunks are allowed to be side by side and free. We merge them or coalesce them into a larger chunk to reduce fragmentation. We don't want all these little chunks all over the place if we can help it. The front end allocator, we don't worry about fragmentation because the idea is the front end services either or small chunk sizes up to a certain value, like 80 bytes that are consistently used, or commonly used chunk sizes. And an example of that would be take a browser, and if you go into CNN.com or MSN.com, and you look at the objects, the HTML objects or elements, you would see lots of span elements, lots of div elements, lots of buttons, tables, title, all these like commonly used HTML elements. Well, every one of those elements has a static size associated with it. So when you look down at the C++ code that actually, and there's a class, every object has its own class associated with it in C++. So if you're talking about a button, there is a C button class. And inside that class are a bunch of member functions, and you've got a constructor and a destructor in there. So you've got a function that's going to call heap create and actually create that element. And then you've got a destructor. And then you've got references being added and released. My point is, since certain HTML elements are going to be used constantly, those will be serviced by the front end allocator because we're not worried about fragmentation because they're constantly being requested. So see how that works? That's why we have a front end and a back end. But then, so it used to be on Microsoft all the way up until Windows 10, the look-aside lists were used in the kernel still, and the low fragmentation heap was not used in the kernel. That was only a user mode thing at first. So you had the kernel pools, like the non-page pools and the page pools, and you had the back-end and front-end allocators, very similar to userland, but the look-aside lists were still used in the kernel. At some point in Windows 10 world, and of course on Windows 11, they brought the low fragmentation heap into the kernel, as well as something called the segment heaps. And it's all a way to kind of protect the heaps and make things more organized. And LFH in the kernel is no longer triggered. It's like it's on by default. But when you get into the world of segment heap, low fragmentation heap, the backend heap, and the various pools, it can get quite complex. So that's like we could have a multi-day class on nothing but that. But like one other thing I'll point out that's a difference, Microsoft or Windows, they consider something called the block size as 8 bytes when you're talking about the heap. So originally you had 120, I think it was 127 or 128 bins on my Windows. I can't remember if it's a 127 or 128 because a lot of allocators have bin 0, and bin 0 holds the chunks. Yeah, I think, shoot, let me do a little math here real quick. So calculator, let's do something here. So 126 times 8, 1008. 127 times 8, 1006. Okay, so in Windows, there's 128 bins because bin 1, you multiply it by the block size, which is 8 bytes, and bin 1 would service and store 8 byte chunks. Bin 100, you would take 100, multiply it by the block size, which is 8. Bin 100 services 800 byte chunks, all the way up to bin 127, which services 1016 byte chunks, because 127 times 8, as you saw, was 1016. That's the largest chunk size supported by the default bins. Any chunk that's 1K or larger would go into bin 0. So bin 0 has these very large chunks, and then you've got, depending on where you are in memory and which allocators, once you get into like over 4 kilobytes, then there's another function that might be used for these very large allocations. And there's a lot of that stuff going on. There's also, on some heap implementations and heap managers, there is something called first fit, which means that when something gets freed, there's a one-time, it basically gets stored in this unsorted bin, and there's this one-time um, allocation where the next allocation that comes in will split that chunk that just got freed into an unsorted bin, and then you get returned to you a pointer to the allocation, and then the remainder gets sorted into the appropriate bin. So I know I just said a lot there, which has nothing to do with off by one vulnerabilities, but you see how easy it is to throw me off and I start going down a rabbit hole. So that's, I think, enough on that topic. But as you heard me just explain, yes, clearly there are very similar things between Windows and Linux and Mac OS and all the other operating systems when it comes to heap allocators. All right, let's get back here. Cool. All right. So what we're going to do now is I'm going to draw up, we're going to write up some code to intentionally introduce a off by one vulnerability. So I'm going to go over to my Linux box here, and we're going to create a file. Let's call it ob1.c. Okay, so let's create. So the first thing I'm going to do is create an example. Yes, this. So. Oh, okay. I'm going to create an example where there's no vulnerability, and then I'm going to introduce the vulnerability due to common coding error. So let's do a simple example. All right, so we're going to say we're just going to set a size of 10, and we'll use this in a moment here. Int main, and then let's think how we want to do this. So off based on size. If I can type today, that'll be helpful. All right, so we've got a buffer here. I'm going to say for set our iterator to 0. So for I equals 0, so here's where the coding error could easily happen. I'm going to say I less than size, right? So while I is less than size, we're going to increment the counter, and we're going to go through this loop. So when we go in here, I'm going to say we want to write into the buffer. Okay, so we'll say buff, which you saw we created earlier, and we're going to write I into the buffer. Simple. And just so we see it on the screen, we'll use printf so we can see what's happening here. And we're just going to print out I. All right, that should be good there. And then we'll turn 0 and close this out. So there's nothing wrong in this code. This should be fine. So let me just go ahead and say gcc ob1.c. All right, that compiled. And if we run it, see how it just prints 0 through 9, and then it stops. There's no vulnerability here. So the problem with off by one vulnerability is, like, if you're familiar with format string vulnerabilities, like if you forget as a programmer to include a format string or identifier, and the compiler doesn't yell at you for that, or you let the warning go, and the user can influence that string that's being passed to printf or printed out by printf, then you can, as the attacker, you can put your own format strings in and cause problems, right? You can potentially exploit the target. The reason I bring that up as an example or comparison is it's really easy to miss them because it doesn't hurt anything if nobody exploits it. Like everything works as planned and everything's fine until somebody finds the vulnerability. Format string bugs are easy to miss, but they're also super easy to patch when you find them. This is a very similar example where you could have this coding error that we're going to put in here right now, and it'll easily be missed until somebody exploits it or finds it. My face was funny when Chompy talked about Ghidra. Yeah, I mean that's definitely a matter of preference there. I mean, obviously, a lot of people like Ghidra because it's free, and a lot of people don't like the fact that IDA Pro is very expensive. But they got a team of developers working on it, and I mean, it's their product. It's like they can charge whatever they want. I mean, it's been around forever, and it's super feature rich, and it's I mean the most mature out there. But when you now have the open source world devoting their cycles to it and everything, obviously Ghidra is going to become a very powerful contender. I mean, I remember first it didn't have debugging and everything in it, but for me, I just don't like the UX of Ghidra. I really don't like the UX. And obviously, with my familiarity with IDA, it's hard to like switch over to something when there's no reason to do so, but it is a fantastic tool. I mean, Binary Ninja is great too. So is Hopper. They're all amazing products. All right, so now I'm going to introduce the vulnerability in here. Why is my cursor not working? Oh, there it goes. Cool. It was not working there for a moment. So now I type in that. All I did was change it from less than to less than or equals. You see the problem, right? I mean, you can see how that would be missed, but you can also see the problem. Less than or equal. That means we're going to allow one more than we should. So if we compile this and now we run it, look what happens. Well, you bring up Vim again. We run it and look what happens. Stack smashing detected. So stack smashing detected because the canary was clearly what was sitting adjacent to the buffer. So in that case, you must have had buffer, canary, save frame pointer, and then return pointer. So we overwrite a byte of the random canary, which means it didn't match up and it caused a problem. That would be an example of an off by one vulnerability. Could you do anything with this one? No, not in this case. I can't imagine what you could do with it. So a lot of times, off by one vulnerabilities you're not going to be able to do anything with, but that's with a lot of bugs out there. Now, off by one vulnerabilities, they typically work on the heap. The heap is when we can do something with this, not on the stack. But I'm just showing you a stack example first, and then we'll look at the heap. Okay, so that's one example. Let's look at another one. And in fact, what if I compile this with the flag minus fno stack protector? So right now I'm turning off stack protection, and I want to see what happens. So look at that. This is what I mean by easy to miss because it didn't cause any problems. The process had no issue. It didn't crash or anything. All I did was turn off stack protection, which means that the off by one vulnerability is overwriting one byte of the frame pointer. Now, can you do anything with that? Probably not in this case, but what if it was a more complex program? Remember what the frame pointer is used for. We pop on all 32-bit processes and on some 64-bit processes, we pop the frame pointer off the stack to point the base pointer back to where it belongs before we did a function call. It restores the base pointer. So if we could overwrite a byte of the frame pointer, we might be able to get the frame pointer to point somewhere where it shouldn't be pointing. I don't know. It could result in some kind of strange behavior. Just thinking outside the box there, right? What sets the canary in the first place? Well, you mean from the compiler perspective, or when you're actually executing the functions? And the compiler, it's just there by default. So stack protection is on by default, and it just inserts the code as part of the epilogue and the prologue of the function. But if you're talking about inside the actual assembly itself, we can look at that real quick if you care to see it. Just waiting for a response on the screen. Again, I don't know why it takes so long for the comments to come through. All right, while you're potentially typing back, I'm going to go and we're going to modify the code to do another example. So there you can see that stack smash and detected again. We're going to do another example now. So let's go back into the code. And let me change this here. So first thing I'm going to do is get rid of this for loop. Most of the stuff's going to stay the same. Let me think here. All right, let's think here. Let me think how I want to do this. We're going to do it this time with a while loop. So I'm going to set my iterator variable outside the loop. So I equals 0. And then I'm going to go into a while loop here. So we'll say while plus plus I is less than size. And that should be it. That's the only code I have to change. Just a different way of doing it. So there's no vulnerability here. Let's see. So I'm going to compile this and let's run it. So no crash there, right? No issue. Let's go back into code. Now here, this is a more common vulnerability that is even easier to miss. So what we did right there is we did plus plus I. What is plus plus I? What does that do? Right? What does plus plus I do? That says we're looking at the unary operator. We're incrementing and then checking. What if we change this to this? Looks harmless, right? All we did was change the increment of the loop from before to after. So pretty crazy that this will cause a problem. Why is it causing a problem? Because the unary operator, if we did it the first way, it's increment then check. The way I just changed it is check then increment. See how that's going to cause a problem? We're actually doing the write and then checking the iterator variable. So we're going to allow us to write one more out of bounds. So if we get out of here and we save this and we compile it, same thing is going to happen. Out of bounds, stack smashing detected because we checked then incremented instead of increment then check. So interesting stuff, but you can see how this stuff's easy to miss. Now what I want to do is we're going to look at a real, well, not like real, but a little program, and there's an off by one vulnerability in it, and I want to see if you can find it. I'm going to let you see it in pseudocode and in disassembly, depending on what your taste is, and see if you can find it. So I'm going to go over to my other system here, and it's on the screen. I know it might be kind of small. You can zoom in if you need to, because I can't display all this code without it being on the screen unless it's a certain size. So on the screen on the left is a disassembly where there's a off by one vulnerability somewhere in there. On the right is the pseudocode, and the vulnerability is there. Same vulnerability, obviously. So I'll just give you a moment and see if you can find it. But yeah, while you're looking at that, we can easily take a look at the way the canary is being set up. Basically, right after the prologue of the function, it grabs the canary from an offset to the GS segment register where the canary is protected and stored as read-only, and it pushes it onto the stack. And then before you hit the epilogue, it checks that canary, it grabs it off the stack and compares it against the stored canary off the GS register and validates that it's still intact. Within while loop, can you elaborate on that, season claims? Within while loop? You're saying the vulnerability is within the while loop? Calling Peter for help. Who's Peter? Peter Van Nickhout? Tell him I said hi. All right. So I know some of you maybe have an idea as to where it is and maybe don't want to say it. You wrote it down. Maybe some people don't know where it is. It is a little bit different than the two examples I just showed you in C code. So the examples we typed up in C code, that would affect the stack in those cases because I had a for loop and a while loop. And in the one example, we did a greater than or equals, which causes a vulnerability. And in the other one, the unary operator, we did the check and then we incremented versus increment and check. Okay, cool. I don't want to spend more time here because we're already like 40 minutes in because I talked too much. Let's look at the vulnerability on the left on the disassembly first. So the problem here is with this call to read. So I'll zoom in a little bit so you can see a little better here. There's a call to read right here, and we're reading into this buffer, right? One byte's getting read into the buffer. If you look lower, we then have this move with zero extend, compare DL. So this is a little check to see if there's a new line character at the end, a 0A, because that's going to kick you out of the program. Otherwise, you're going to go into this loop. We're also checking if there's a null byte. But we go into this loop then, and look what we're doing. We're reading into the buffer. We've got our iterator that we'd be incrementing. And you could see we're reading into the buffer in this loop, but we've already read one byte into that buffer up here. So we read a byte into the buffer, then we went into a loop, and we're running into a problem. So look over on the right. It's easier to see on the right. You've got the call to read right here. So we're reading a byte into the buffer. And then right here, we see we're going into that while loop. We've got our iterator, buffer not equal to 10. We're just going to run through this loop. So we're reading in an extra byte into the buffer because we did one read outside the buffer. Does read increase the offset into the file stream? Yes, you could see it increments. So you're going to go 1 byte over each time, yes, into the buffer. But that's where the vulnerability is. So what I want to do though with this is let's go over onto the Linux box and let's see this thing, what it looks like inside the process. So I'm going to go back over to my Ubuntu VM here. And we've got this, you may have heard me talk about that program before, Baby Heap. We're not going to go through the whole Baby Heap vulnerability because that's just time consuming. I think I did it a long time ago anyway, but it's basically there's a memory leak that you've got to cause, and then you've got to exploit the off by one vulnerability that you just saw. Now, it's tricky to exploit these off by one vulnerabilities. You've got to have some good familiarity with how the heap works and how things like Tcache bins work. And the interesting part is I'm not sure what libc version we're on right now, like 2.39, 2.42. I have somewhere up there. But Ubuntu and the other various flavors, they don't typically go on to the brand new version. They wait until it's stable a bit. And as we know, it's an even bigger problem with the world of Linux than it is on Windows. There are thousands of different flavors and versions of Linux Unix out there in the world. I mean, and I'm not talking just about like Gentoo versus Red Hat versus Solaris versus Dynix versus SCO versus I don't know, whatever else. I mean, there's so many of them, but you've also got all the different kernel versions there. You still see sometimes kernel 2.6 on airplanes, on IoT devices out there. So all kinds of crazy stuff, right? The reason I'm saying that is because you have a lot more opportunity for getting exploitation working on Linux than you do on Windows in a lot of cases, because just because you run across a system that might be on libc 2.42 and is not vulnerable to something that was 2.36, there are still tens of millions of systems out there running older. And not just that, almost every time a new version of libc comes out, one of the things they'll go in is they'll go in and mess around with the Tcache bins and how basically the optimization is working. And there's that big question that has to be asked a lot, which is performance versus security. So are we really worried about someone exploiting this obscure thing? Or would we rather have performance being a lot higher? So there's a lot of questions that have to be answered. And it's quite fascinating. Like as soon as we put this particular technique into the one course that I have, 760, a new version of libc came out. And guess what? This technique didn't work, but if you make one little change to your exploit, it works again. And then another version came out. You make one little change to it, it works again. So it's a little bit of a cat and mouse game a lot of the time. Anyway, let's look at this. So what I've got here is a Python script that's my exploit, and this exploit is actually the full working exploit to exploit this vulnerability. We're not really worried about that in this session. What we want to do is look at the off by one vulnerability specifically and why it's problematic or why it can help us. And it gets a little tricky. So let's first I'll show you the program. So if we run the program, it just says yet another baby heap, malloc, free, show, exit. We could say, okay, I'd like to malloc. And it says size, 100, content. How about a bunch of A's? Okay, so I'll say then show me which chunk. Well, we only did one, so obviously it's going to be 0. And it just shows us the A's that are inside that chunk. So it's just a little basic program that utilizes the heap and has an off by one vulnerability inside of it. So you would really have to go back and forth between IDA or Ghidra or whatever and experimenting with the program to figure out what it is that you can and cannot do. There ends up being a situation here, and I'll show it to you real quick if I can find it. Higher up in this code, like up here, see how it says add hex 10 to rex. Actually, I don't think that's what I'm looking for. This right here is what I'm looking for. Compare what's in EBP against 9, and here we add 1 to EBP. So it's basically a little loop, and it's going to let you continue to do something until you hit the maximum number. And it says compare EBP to 9, jump if above. So what that ends up being is we can only do a certain number of allocations before the process kicks us out. Now, we can do a bunch of allocations and then free some of those allocations and then do more allocations to keep the program running, but we're only allowed to have a certain number of allocations out there at once. So we keep that in mind when we're messing around with the program. So what I'm going to do now is we're going to bring up the exploit, and we'll look at a couple things in here. So this is using Pwn tools, which is a cool, basically Python library that is really helpful with capture the flag vulnerabilities for the most part. You typically don't use them in real world exploitation. But allows you to do some things really easily that would otherwise take a lot more code and be a lot more painful. So you can see what we've created here are multiple functions. These little functions, malloc, free, show, they basically emulate what the user input would be if you were typing in the commands to the target program. And this allows us to automate it, right? So we can call these functions and we could do allocations and such. So down here a little bit further, you can see I've got a little if statement that says if args or GDB attached to it. So we're going to use that. So when we run the program and we put GDB afterward, we'll actually attach to the process and we'll be able to examine what's going on. Now, below here, you could see I'm saying for I in range 7, malloc 178. Now, the reason we're doing 178 here and F8 down here is because this program, if you look at it, has a little check. It has a little check. You can see it says size right there because it's asking you to enter in a size. Right here, it says compare basically what you entered in register 12 to F8. Jump if below or equal. So if the size that you requested to allocate is below or equal F8, you're going to take the jump over to the right and it's going to do a allocation of F8. So even if you put in a size of 1 or 2 or 20, you're going to get an allocation of F8. That's the default size it uses, unless what you enter in is bigger than F8. If it's bigger than F8, you're going to go over here to the left, and it's going to do a default allocation of size 178 hex. So that's like when you're studying a process, especially like a capture to flag, this is the kind of stuff you're looking at. I mean, this is going to end up being a constraint that we would have to oblige, we have to stick with it. There's also a check a little bit higher. It says right here, if you enter something in that's greater than 178, it kicks you out. So you've got some limitations here as to what sizes you can allocate. This is going to end up being important. And this is not something that's uncommon in a lot of programs out there because If a developer of a program has the power to and desire to help with fragmentation and try to keep things clean, they could theoretically make it so all allocations are of a certain set, a size set. That way, if something gets freed, we know that it will get taken up pretty quickly because it's always the same sizes that are being used. I'm not saying this is very common, but it does happen. So either way, those are the allocations that are going to happen. So let's go back over here to the process. So that's why we're doing this. Now, the first thing we're doing, now the reason you can see we're doing 7 allocations up here. We're doing another allocation of the same size here. We're doing one more allocation of the same size there. That's 9 allocations. And the reason for that is because you saw in the code, we can only have a maximum of 9. If it's above 9, it kicks us out. So that's one of our limitations with this example. You could bypass that check, right? Sign comparison jump below or equal. Well, I don't want to spend time on that, but if you go back over, you can see that it actually does a little thing here where it says up at the top, load the effective address RAX -1, so it subtracts 1, and that's why the comparison is to 177 versus 178. So it's doing some weird things. I mean, there might be a possibility to bypass and get a larger size, but I'm pretty sure it'll just kick you out. All right, so back over here, we've 9 allocations. Now, a couple weird things. The reason that we are doing this final allocation is because there's something on the heap called the wilderness chunk or the top chunk. You can call it either. It was called the wilderness chunk because the joke is that once you hit the top of the heap, if you look out past that point, it's like the jungle, right? There, way far away is going to be the stack potentially, multiple gigabytes away. But if you're at the top chunk on the heap, it's called a wilderness because it's all unmapped memory. It's all virtual memory addressing that has no page tables associated with it. So the reason that we are allocating this chunk and we're going to leave it there is so that we don't coalesce. If coalescing happens when we don't want it to happen, it ruins our exploit. So that's where your knowledge of how things like the top chunk works, how coalescing works, how the front end versus back end, all that stuff, that's where that comes into play. So just know that's why we're doing that 9th allocation. After we do those 9 allocations, we're freeing 8 of them. We're leaving the top chunk, that's the wilderness chunk there, but in this example, we're freeing all 8. And the reason that we're doing this is the default for Tcache bins. If you look at the source code in libc, the Tcache bin default maximum number of chunks per Tcache bin is 7. You can only hold a maximum of 7 chunks in a Tcache bin. That means what happens if there is an 8th chunk of a specific size that gets freed and the Tcache bin is full because it already has 7 chunks. That 8th chunk is probably going to go to the unsorted bin at first, but then it's probably going to go to the back end doubly linked heap. It's going to go to the back end heap. Because remember, the idea behind these Tcache bins is that each thread gets its own set of bins to service chunk sizes that it doesn't have to worry about having that global mutex in order to be able to get that allocation. So just some examples here. Some of this stuff that you see in the code is irrelevant to the specific thing that I'm talking to. Like, for example, this right here, this is leaking out a memory address. And the reason this is working is because chunks, when they're freed, they get something called forward pointers and sometimes backward pointers, depending if it's on a front end heap or a Tcache bin, or if it's on a back end heap. If it's in a back end heap, it's part of a doubly linked free list. So it's going to have a forward pointer and a backward pointer. And if it's on a front end allocator or a Tcache, it's going to have one pointer, just a forward pointer. But the cool thing is if you have a chunk that you have requested and returned back to you is a pointer to that chunk that you requested. If you don't write anything into that chunk, and it hasn't been mem set to 0, which it never is. Calc is hardly ever used, and you hardly ever see mem set. This is what we get into a lot of problems. Remember way back in Heartbleed? That was one of the problems there. We're not mem setting things out. We're leaving old data around. Why this old data becomes useful to us is because the old data is a pointer. And the thing that it's pointing to oftentimes is at a static relative offset from the base of libc. That's your ASLR bypass right there. So if you can leak out an old pointer that was part of the heap, you might be able to bypass ASLR, and it's a very common way that we do that. But that's not part of this specific thing that we're doing here. What we're looking at is up on the screen now. See where it says Tcache poisoning attack? So we're saying malloc 234. Now the 2, 3s, and 4s are irrelevant. That's just for us to, like, when we see those numbers in memory, we know which chunk it is. But we're allocating 3 chunks, and then we're freeing the last chunk first and then the first chunk, leaving the middle chunk in use. This is really important, the part that I'm about to get into now, because this is why a off by one vulnerability can potentially be exploitable, and it's tricky. So we're doing something called heap grooming. Heap grooming can be a lot of different things. Like basically, when you're massaging or grooming the heap, it's, in my opinion, anytime you're doing anything so that you control the layout of the heap. So um, position independently what the layout of the heap is, because ASLR is always going to be on. So we don't even want to have to like think about that. We want to know that relative to where we are in memory, we know where our things are at. We know what's there, and that's all that matters. So we've done 3 allocations of a smaller size. Remember, there's only 2 sizes we can use, F8 and 178. We're intentionally doing these small sizes. We free the last one first, and then we're going to free the first one. The middle guy stays in use. That off by one vulnerability we saw is going to allow us to write 1 byte out of bounds, 1 byte past this chunk on the heap. Now, I'm going to draw something up real quick to help those of you who have a Linux heap background. There are different allocators out there, like you've got old ones like DL malloc, you've got PT malloc 2, which is the most common one still out there. You've got TC malloc, which is Google's thread caching malloc, PHK malloc. You've got JE malloc, which is Jason Evans malloc. They hired him at Facebook, and he was there. In class, I usually talk about why they brought Jason Evans in, because he was able to get a 3% performance increase. And when you're talking about 10 million servers, a 3% increase is a lot of money. And it's all about, everybody thinks they can do a better job. Like anytime somebody says, I'm going to write my own heap allocator, it's because they think they can do a better job than the other ones out there, or maybe they're trying to accomplish something that the other ones don't do. Like, for example, JE malloc is going to sacrifice a little bit of security in trade for performance. And a lot of that has to do with the order in which allocations come from a free list. If we do a last in, first out, that's always going to be a vulnerability, because the attacker knows that what they just freed is going to be immediately returned back to us from a next allocation request of that size. Versus random allocations from a free list is going to make it more difficult for an attacker to predict what they're going to get in return, which means they're going to use things like plunger technique and all to flush the chunks. All right, so let's look at 2 examples. The first one's going to be DL malloc, which is an older one, and you'll see why I'm going to show you this in a second. And the second one's going to be PT malloc. Now let's say that you've got, let me write that on the side. So this is DL malloc. My handwriting's beautiful, isn't it? PT malloc 2. Now this is going to be at the top of the chunk is going to be the metadata. Now this is going to be in DL-malloc world. This is the previous size field, and below it is going to be the size. Now on PT-malloc, it's more like this. You've got the size, and you don't have a previous size field until it's needed. That's the trick. So if we were to draw an adjacent chunk down here at the bottom, so let's say this is an adjacent chunk in memory. In the world of DL-malloc, the previous size field is always going to be there. This is going to be important. That's why I'm explaining it, not just boring you. Well, I might be boring you, but it still has a purpose. Previous size. So actually, in this case, it's more like this, size. So again, that's DL-malloc versus PT-malloc. And this is the metadata. So there's the chunk pointer and there's the metadata. When you call malloc, so if you say malloc 80 bytes, what you're going to get a pointer to is right here. It's the start of the data. That's what your pointer is. Now, when both of these is what Windows 7, what I'm drawing, no, this is all Linux. This is DL-malloc Linux heap allocator versus PT-malloc Linux allocator. So when you call malloc, you get a pointer returned back to you, which is the start of the data. Now, in the case where both of these chunks are in use, then great, they're both in use. But even when a chunk is in use in the world of DL-malloc, this previous size field is still there. It's there. In the world of PT-malloc 2, if these chunks are in use, there is no previous size field. The previous size field doesn't exist until the chunk gets freed. So, for example, if this chunk right here gets freed, then the last 8 bytes, if it's 64-bit, of the data of that chunk that's been freed turns into the previous size field. See how that works? As we're on DL-malloc, it's always there. On DL-malloc, it's always 0. Unless the chunk adjacent lower memory has been freed, then it will be populated by the free function. But in the world of PT-malloc 2, they wanted to optimize it so that we're not wasting space. That's the whole reason for this. If you look at DL-malloc, you're like, well, why are we wasting those 8 bytes of memory for a field that's not even needed most of the time? So in PT-malloc 2, let's not do that. Let's make it so we only create that field if the chunk gets freed. Then the last 8 bytes of the chunk that's freed becomes the previous size. This is really important to the off by one, because if we were able to exploit the off by one, so I'm going to put OB1 in DL-malloc. If we could exploit the off by one here, look what we're overwriting. We're overwriting this byte right there, the lowest byte of the previous size field, which is always 0. That doesn't get us anything. And this is an older allocator. So DL-malloc, you never see it anymore. PT-malloc 2, remember how it works. If we exploit an off by one, we're overwriting the lowest byte of the size field. That's a big difference because that actually is a variable that is important. And if we can overwrite a byte of the size field, this is the key part, we can then free the chunk that's had an overwritten byte and make it go back into the wrong bin. Think about that. These are T-cache bins we're talking about. The T-cache bins, there's going to be one for each size. If I can overwrite a byte of the size variable and that chunk gets freed, it's going to get returned to the wrong bin. And you might say, okay, well, why is that important? Good question. The reason it's important is because then when we do an allocation, the heap manager itself, it still thinks that it's a chunk of a certain size, but we've messed with it. So it's in the wrong bin. So then the next allocation comes out of the wrong bin. It thinks it's a size that's bigger than it really is. which is going to allow us to overwrite things. And we have a heap overflow vulnerability now due to an off by one attack. So, and you're going to see this in the debugger here in a moment, because I know it's hard to like visualize. But to summarize, we are exploiting an off by one vulnerability to overwrite the size field of an adjacent chunk in memory so that when it gets freed, it goes into the wrong Tcache bin. It's not really that big. We're going to lie and make it look like it's bigger than it really is, so that when it returns back to us from the wrong bin, we're going to be able to do a heap overflow, and we're going to be able to overwrite something that's very important, resulting in code execution. So let's look at this in a debugger. So what I want to do is set some breakpoints here to show you some interesting stuff. Let me think where I want to do it here. So if we do these allocations, great. If we free 4 and free 2, we'll have that middle chunk. All right, let me do a couple pauses here. So what I'm going to do is I'm going to start the process. It's going to dynamically send in all this stuff, and then it's going to pause right after it does these 3 allocations for us. It's going to pause, and then we're going to take a look at the heap at that moment in time. Then I'm going to tell it to continue execution. It's going to free 4, free 2, and then we're going to look at what that results in. And we're going to go through this piece by piece so that you can see why this is going to result in code execution. All right, so let's try it. All right, so we're going to say Python exploit.py, GDB is my argument. So you can use tmux if you want to split the screen. I like having separate screens. Everybody's got their taste. So right here on the left side, you can see that I'm in the debugger. It attached automatically due to those arguments. And we've got Jeff here. Instead of PETA, we're using Jeff for our exploitation assistant. The reason I like Jeff in this case is because we can use simple commands like heap chunks and heap bins, and it shows us the stuff. So we've just attached. So I'm going to go ahead and say continue. And what's happened now is it's paused execution based on that specific spot we told it. This is right after we've allocated those 3 chunks of that certain size. And then the next pause is going to be after we freed 2 of them. Is the 2-bin multi-bin also called Kanban system? Is that something? Uh, I'm honestly not sure. I haven't heard that terminology, the Kanban system, in relation to this. So sorry, I don't want to give you a wrong answer. If you find it out there, let me know. I'm curious. So right now, I'm going to pause execution in the debugger. So we're stopped, and I'm going to use the command heap bins. So with heap bins, this is showing us all the different bin types. We've got the unsorted bin, we've got the fast bins. Here's the Tcache bins up top. So you can see right now we've got 6 entries in the Tcache bin for size 170. The maximum it can hold is 7. And there's a reason as to why we're playing with the numbers in this case, because we need to make sure we understand how many chunks are in each bin so that we know where things are going to get, where they're going to go when they get freed. Cool. Thanks, Albert. Yep, it's being recorded. It'll be on YouTube right after I get done here. Cool. I don't know, 660 when I'm teaching it next. I might be going to London coming up in a couple months. We'll see. It's up on the SANS website there. You can check it out. All right, so right now, though, we've done those 3 allocations. So next thing I'm going to do is say heap chunks. So when we do heap chunks, here is the 2, 3, and the 4, because 32 is hexadecimal ASCII for 2, 33 is 3, 34 is 3. So remember in the code, we intentionally allocated the first byte of each of these chunks to be 2, 3, and 4. These are currently in use right now. The next thing that's going to happen, and here's that top chunk that we're leaving alone. The next thing that's going to happen is we're going to free this guy on the bottom. We're going to free this guy on the top, and we're going to leave this one in use. So let's see what the difference is. I'm going to say continue. Continue. We paused again. You can see we did free 4 and free 2. This is using Pwn tools with the logging to the console. That's why it's printing that out. We're going to go and pause again. And now when we look at heap chunks, see how the only one that remains is 3, 3. Now the other guys are still there. You can see size 100, 100, 100. They're still there, but they're part of a bin now. So if we go and say heap bins Tcache, you can see that there are now 2 chunks of size F0. Before, there were only 6 chunks of size 170, but now we've got 2 chunks of size F0. So it's mapping exactly to what we want it to do in the code. So at this point, I'm going to go back to the exploit code, and we're going to look at what we want to see next. So let me kill this. So bring it back up in Vim. So I'm going to get rid of this guy. Now we're still going to pause after we free those 2 chunks, leaving the chunk in the middle still there. Look at the next thing that's going to happen. I'm allocating size F8, filling it with Z's or Z's times including an additional one. So see that? We're doing the size F8 plus 1 additional one. This is really important because this is the off by one they're exploiting right here. That's why we're allowed to write this extra byte. And remember what we're overwriting. We are overwriting 1 byte, the lowest byte of the size field of an adjacent chunk in memory. We are changing it from 00 to 1 to adding the 80 on the end. So you'll see what happens here. Let me pause. Right here, you're going to see it. Pause. This is a really cool part. So we run this. And right now, heap chunks. Heap chunks. So here's that middle chunk that's still allocated, right? Now, we need to do something interesting here. Now, remember what happened. We freed chunk 4, then we freed chunk 2. Chunk 2 is this guy up here. When we now do an allocation, which is what we're doing right now, when we do an allocation, it's going to get returned to it this pointer that I've got highlighted. We're exploiting the off by one. We want to change this size from 100 to 181. We want to overwrite that byte, tricking it. So I'm going to take a look at this pointer here. So we're going to say x/4gx, G is giant for 64-bit, starting at that address, plus 100, which is the size, minus 8 bytes, which gets us to the size field. And see what it says right there, 101? It says 101, right? That is the size field of the middle chunk, chunk 3. Watch what happens now when we exploit the off by one. Now we allocated those Z's plus an extra one to exploit the off by one. And now watch. We look at that exact same chunk and it didn't do anything. Isn't that brilliant that I showed you that it did nothing? I mean, I just wanted to impress you and show you that nothing happened here. No, I'm just kidding. So watch what happens here. If we go and say plus 0x100 minus 8, let's see here, 0x100 minus 8, we get to that guy. All right, give me 1 second. I think I set the pause in the wrong spot. My apologies. Give me a moment. When we free it, it's going to go to the wrong bin. All right, let's do it here. All right, let's try it again. Run it. Now we are at the point where we did we freed the 2 allocations. So let's just double check that everything's looking right. And let me check my math and stuff again. All right, so we are there. We're going to pause. We're going to say heap chunks. I'm not sure why it's hanging right now. That concerns me a little bit that it's hanging. It should not be doing this. Okay, seems happier now. So there's the 3, 3. That's that middle chunk, right? This up here is going to be the chunk 2, chunk 3, chunk 4. And what I did before is I grabbed this address here. I might have grabbed the wrong one, but let's grab this one first. Copy that guy. and we're going to say x/4gx, that address, plus 0x100 minus 8. And we see 101. Let me check one more thing. That plus 0x100 minus 8. And we see 101. So what I've just done is we started at chunk 2. We looked at chunk 3's, the middle chunk size field, it's 101. And we looked at chunk 4's size field, it's 101. And now I'm going to continue, and we're going to let it do the allocation of the z's, hopefully exploiting the off by one vulnerability. So we're going to say continue, and here I'm going to say continue. So now we're there. Break. Now let's look at the first one, and there it is. So it did work. I don't know why the first time it didn't show me. I think it's just like the debugger was screwed up because I didn't do anything different here except for change the pause until after the free, which probably helped. Yes, I do make mistakes all the time. So, but do you see what happened? We just enlarged the chunk. We lied. We tricked it. We changed it from 101 to 181, which means that since we just freed this chunk, it went into the wrong bin. So let's take a look at the bins. Heap, bins, tcache. And look at that. The size is now 7. It was 6. So the chunk that just got freed is in the wrong bin. Now these are the most important parts of this explanation. What I just talked about was the first important part, that we exploit the off by one so that we overwrite the size field of an adjacent chunk and free it back into the wrong tcache bin. Here is now the reason why this is going to be problematic. When I do a malloc now of the larger size, it's going to return last in, first out. I'm going to get the enlarged chunk. Remember, that chunk is not really that big. It's being returned back to me now, which means I'm going to be able to overrun the true size, which is F0, and I'm going to be able to overwrite the pointers of that chunk. This is the tricky part. This is the really tricky part. Let me draw out what's happening here. So we have multiple chunks, 3 chunks. We've got chunk 1, we'll call them 2, 3, and 4 because that's what we're using, right? So we've got 2, 3, 4. First thing, and let's put them all in use right now. In use, in use, in use, right? They're all in use. What we then did is we freed this guy first, and then we freed that guy. And remember, these are all of size F0. What we then did is we did a malloc, and we wrote Z times F0, whatever it was, F8, F0, I can't remember the exact size. I think it's F8 actually, plus 1. That allowed us to overwrite this with 8-1 instead of 0-1. It was, let me write that. This right here, the lowest byte of the size field, size, was 0-1. We exploit the off by 1 and we change that to 8-1. Then we free this guy. That guy gets freed. It goes into the wrong tcache bin. So this guy gets freed, goes into wrong tcache. When we then do a malloc of the bigger size, it returns us back this whole thing. It returns us back more than it was supposed to. What we're then going to do, this is the nasty part, we're going to overwrite the offset where its pointers were. That's supposed to be where the pointer is. Remember how tcache bins work? They have a forward pointer that points to the next one on the list. We are going to, the first thing I'm going to do is write dead code here. And then the next thing I'm going to do is write something called free hook. I'm going to write to the address of free hook. Free hook is a special hook that the developers of malloc put in, that anytime malloc is called or realloc is called or free is called, there's a hooking opportunity for debugging purposes. So if something exists in the free hook position, it's normally going to be 0. If something exists there, it will call whatever that address is and execute it. Normally, there's nothing there. If there's something there, default behavior, it will call the address that's there. What we want to do is exploit this off by one vulnerability like we are to do the heap overflow to use the address of free hook that will then get written into the Tcache bin. The free hook address gets written into Tcache. That gets returned back to us, allowing us to allocate whatever we want into the free hook variable. We're going to write dead code there, meaning that the next time we call free, we get code execution. Pretty neat, right? So let's do this. And I know that's a lot. That's a lot of weird stuff going on there. So at this point right now, we've sent the enlarged chunk due to the off by one back to the wrong Tcache bin. The next allocation of this size is going to return our fake enlarged chunk, allowing us to do that heap overflow. So let's validate a bit of this. Let me see if I can see something right now. So see this right here? That is the forward pointer that resides at that location. So if we take a look at this, it's probably just the next one on the free list. Is it up there actually? Let's see. So 81010. 81010. I was looking around at these addresses up here, but let's see if there's anything here. What is this? Let's say it's just another chunk. So what we want to do is overwrite this pointer here with the address of something we control. The first thing I'm going to do is use dead code, and watch what happens here. I want to see dead code get written up into the Tcache bins. So let's drop out of here, and let's go up into our exploit. Let's get rid of this first pause. So right now we're only pausing after we've freed the enlarged chunk. The next thing I'm going to do here is I'm going to comment that out, and we're going to malloc dead code. So what we're doing is we're mallocing a large chunk. This is going to return back to us the fake chunk that we enlarged, and we're going to write hex 100Bs to get us to the point where the forward pointer is located. We're going to write dead code in that position. Then when that gets allocated, we should see dead code get written into the Tcache bin, proving that we're at the next step. So let's go ahead and I'm going to set a break here. And we'll set one more after this malloc here. All right, let's go. All right. And let's see where we're at. So heap bins. Tcache. And you can see we've got 7 chunks currently in there because this is right after we freed our fake chunk. So great, we see that's there. Now let's take a look at that pointer right now because we're about to overwrite it. So let's grab this chunk here. 4.3, so that means 4.2 is up here, 4.3 is here. So if I grab this chunk here and we say x/4gx, that address plus 0x100 or 0x100, let's see what's there. Okay, what about -8? Cool. So let's now say continue. We malloced, let's break. Now let's check and see what's there. How about plus 0x100, that guy? So there's our 5As. There's our Zs. Okay, and what we just did was we malloced that large value. Let's go in and take a look at another terminal real quick so I can see my code again. So ob1 vim exploit.py. Okay, we are at the point. What we just did was we freed 4 and freed 2. We then wrote our Z's to enlarge the chunk. That was our first pause here after we enlarged the chunk. Send it back to the Tcache bin because we freed it. Now we just malloced B times hex100 dead code, dead code. So that's what we're looking for now. So I just wanted to recheck and see where I'm at. All right, so there's our Z's. Let's go look at heap chunks. There's our B's down here, size 180. So let's take a look at that address. x/4gx, this address, plus 100. There's dead code, dead code. So that's the forward pointer we were looking for. The reason I went back and looked at the code is just to make sure that I remember the numbers correctly, because we've screwed all this up. That's why it doesn't look very nice anymore, but we can see our Z's and we can see our B's down here. This is the fake chunk size of 180. What we just checked here is that because it used to be size F8 instead of 180, we looked at the appropriate offset where the forward pointer should be at. So what this was a pointer to another chunk on the Tcache bin. But now we've overwritten it with dead code, dead code. So if we look at the Tcache bin, dead code's not going to be there yet. So heap bins Tcache, I don't think it is anyway. Oh, it is. Okay, it says corrupted chunk, but it's not officially in the list yet. Now, if I say continue, we hit the next pause. Let's take a look at the Tcache bin now. Perfect. See how it went up a notch right there? Corrupted chunk. Before it was down here. And now we're at the top of the Tcache bin, and it's the next thing to go. So basically, if we do another allocation request at this moment in time, we're going to get back the address of dead code, dead code. We don't want that, but we're proving something. What I want to do, and here's the cool part, I'm going to say what is at freehook right now. So we'll say print, actually x/gx, what is at the address of freehook? 0, nothing's there right now, because that's the way it normally is unless someone's intentionally hooking. What I'm going to do is instead of putting dead code into the forward pointer into the Tcache bin, I'm going to put the address of freehook so that the next allocation out of this bin returns back to us this address of freehook, and we're going to write dead code there so that when we then go to call free, we're going to get code execution because the instruction pointer is going to go to dead code. That's our goal. So let's kill this. All right, so now we're going to do this. Let's get rid of this pause here. And let's pause. Let's take that guy, and then let's not do this. So what we're going to do then is now malloc. This malloc call is going to return back to us the address of freehook, and we're going to write dead code into the freehook address. Then when this call to free happens, it's going to call dead code because of the hook. That's where we're at. So we've got how many pauses? We're going to pause one time, and then we're going to go. Perfect. Okay, let's go. Now we're going to say Python exploit GDB. So now we paused. So I'm going to Control C. Let's take a look at things. Heap chunks. Here's our B. So we're going to take this address, copy that. We're going to say x/4gx, this address, plus 0x100. And see how we wrote dead code? That's because I didn't update it. I got to go fix my code. Shoot. Glad I caught that now, though, because that would have been annoying if I didn't catch it now. So what I forgot to do is this right here. Oops, malloc that, and then we're going to say comment that out and remove that comment. See, I'm changing it from writing dead code into the pointer to the address of free hook. That's what we're doing here. That's all we're doing. So now let's run it again. All right, let's take a look now. Um, heap chunks, this address here. Now, instead of dead code, it should show us the address of free hook there because of our code change. So we're going to say x/4gx, this address, plus 0x100. And there's the address of free hook. Now, if we look at the address of free hook right now, so look at that address I've got highlighted, and then look at this. We're going to say x/gx, address of free hook. See how it's the same address? So that means the next malloc allocation is going to return back to us this address. We're going to write dead code right there. So watch what happens. Continue. And it crashed. It crashed because look at free hook. Dead code is there. Look at the instruction where we're at. We are at jump racks is the code. Well, what's in racks? Dead code. So we have now effectively gotten code execution, but it's not actually going to that address because it's not a legit address. So for exploitation, what we do is we, instead of writing dead code here, we would write the one gadget address, which is, if you're not familiar with one gadgets, it's a magical gadget that pops a shell with a single sequence of bytes. So if you want to see the actual completion there, if we kill this, bring up the exploit again. So if I change this now, I'm going to pause. I'm going to pause right here. So there's two pauses. Run it. Tell it to continue. And then we're going to do the same thing real quick. Heap chunks. Grab this address. Plus 0x100. And there's the address of free hook again, right? So x/gx, address of free hook. Nothing's there right now. I'm going to say continue. We break. Now at that location is the address of a one gadget. So if we look at this guy here, and I say examine the instructions at this address, it's a magical gadget that's calling execve, and it's going to pop a shell. It's going to load a pointer to bin sh and pass that to execve. So if we let this run, it's going to execute that. Let me see if I can break on this address here. It might not let me, but I'll try. Break. Continue. Did we hit the breakpoint? Yeah, we hit the breakpoint. So where are we now? You can see down at the bottom, we popped the shell already. So I don't think it's going to let us see it, what I wanted to see. Move RSI, RCX, execve. Yeah, so it did stop there. So you could see what's going to happen is we're going to call execve, and there should be a pointer to bin sh somewhere. Maybe it's at this offset here. Let's check that offset and see if it's there. Yeah, see that? Isn't that cool? Bin sh magically is just in this code sequence getting passed and calling execve, and that's why we popped that shell. So we're done, but we popped the shell. Pretty neat, right? It's a pretty cool exploit. Yeah, that offset to whatever the registers were at was a pointer to bin sh, yes. Why are we using the strip function? Oh, probably to deal with the zeros to get rid of the null bytes is if I remember correctly without looking at it. All right. Whew, that was a bit of a whirlwind. Took us longer than I thought, an hour and a half, but these things never go fast. But it's fun, right? I mean, it's kind of neat. I haven't done this one in a while, so that's why I was kind of putzing around a bit. But it's neat to go through that because you really get to understand that like simple little things, like even overwriting one single byte in memory can potentially yield you code execution eventually, which is pretty wild. So that is the end of our stream today. Thank you for participating. Have a great weekend. And next week, like I said, we got Jonathan Ryder. He'll be on showing us some neat kernel debugging stuff, probably some C2 stuff with the life of a packet. And then 2 weeks from today, we've got the folks from BC Security on Beyond PowerShell, and they're going to give away a free course. So be there for that one if you want a chance at winning the free course. And otherwise, have a great weekend. See ya.